first guest speaker, William Kennedy. William is a Potsdam alumni, class of '91, as you also know, a judge for our event. The SUNY Potsdam ACM met Bill at the Capital Region Google Developer Group. William is a managing partner at Arden Studio in Miami, Florida, a mobile, web, and systems development company. He's also the author of the book Go in Action, the author of the blog goandgo.net, and a founding member of GoBridge, which is working to increase Go adoption through diversity. William is one of the most passionate speakers that I've ever seen in my entire life. First time I saw Bill talk, I was just truly blown away. He speaks with so much energy and livelihood, and it's truly an honor to have him here joining us today. Without further ado, please join me in welcoming Bill.
Thank you for taking some time here. Where are we? Coming out, I know you guys are here to hack some really cool stuff. And I'm here to ask questions during the day. If you want ideas around architecture and design, hit me up. Okay, so how many of you want to be back server developers, right? Because you hear about front end and you hear about back end, and anybody who says they're full stack is a lying piece of, I won't say it. Right? Very, very few people can really say they've mastered the entire full stack. And you really don't want to do that anyway. So who's really here saying, you know what, I want to build air conditioners, I want to build that server code on the back end? Wow, don't all raise your hand at once. All you guys want to be front end developers then, is that what it is? You guys want to be in the limelight? You want to show your stuff and somebody just nitpick and complain about it all day? Because at the end of the day, you guys all better get used to just being told your shit sucks. Because that's what it is, a constant reminder that we can't write code that just works, especially on the front end. Oh my God, I hate the front end. In fact, I'm so bad with design, I'm not even allowed to talk to my own designers, who I've hired in my company. Right? Okay, but I'm a back-end developer. I build those systems that I always say air conditioners. You don't know they're running until they break. And we're dealing with scale today, right? Everybody wants to write software that's at Google scale. There's very few companies that have to deal with Google scale. But Go is coming out of Google out of the need of replacing 15 to 16 years of C legacy code that has become so big it's become almost impossible to maintain. And so that's where this language is coming out of. Anytime you choose a language that you want to learn or work with, I want you to look at the origin of that language. I want you to understand why somebody took the time to write this language. Because there has to be a purpose for that. They woke up one day and said, the languages we have today are not good enough for this problem. And so Go is about Google scale problems. Too many people are trying to write Google scale solutions day one. So we've got to stop that. So there's going to be two parts to this talk. I want to give you, I'm really big about design. I'm really big about design and thinking about the systems that you need to build and doing it a little bit at a time, but I want to give you some ideas around if you really wanted to sit down and start building software that can scale. The mistakes that I see all the time when people start out these projects. That way you can start thinking about the things you need in your software now and not make the same mistakes I see over and over and over again. Now in the second half, I'm going to show you some cool, because it's a hackathon, we got to show some code. Some cool constructs in Go around what concurrency really is as part of the language. We'll talk about something called channels, which allows you to coordinate independent pieces of processing. Before we had this in Go, everything was around what? Mutexes and atomic functions. And it's really hard to coordinate threads when you're using those constructs. So I'll show you some really cool things in Go around channels. Hopefully get you a little bit excited about the language, all right? So let's start with that. Okay, so a few things here. You've decided that you want to go and you want to write a server now that can handle hundreds of thousands of concurrent requests, right? I mean, this is the dream. This is what we want to be able to do. We want to be able to scale that out in data centers over the cloud and stuff. Okay, great. But how do you start? Forget about the code and forget about the language. How do you start to build a piece of software like this? There's three things that I see over and over again in industry that people are missing over and over again. So here's the first rule of writing software that can handle load. 1, your software has to be able to start up cleanly, and yes, shut down cleanly, even under load. I don't care if you're handling 100,000 requests a second, I should be able to signal that piece of software, and it's got to be able to shut down. Think about it. If you have to issue a kill 9 every time you want to replace your server, what is happening during the time that that thing is shutting down? Are we corrupting file systems? Are we corrupting databases? The big systems today for orchestration, you guys have heard of Kubernetes, okay, Swarm. You've heard of these things? They all require the ability for you to go get that piece of software you're writing, get it out there in production, and do it with a level of integrity. Now, if you don't do this from day one, if you don't from day one start turning your servers on and shutting them down, signaling them in some capacity, control C, whatever, it's not going to happen. It's just not going to happen. This is not something you can get to later. I'm going to tell you some really bad stories around this in a second. That's number 1. I'm giving you guys something that I usually talk about over a period of a couple hours in about 20 minutes here. Number 2, back pressure. Now, what is back pressure? Back pressure is a key component to system and architecture design. Back pressure can be a very good thing, and it can be a very, very bad thing. So think about it. You got 10,000 requests coming into your server, and everything's going great. It takes 1/10 of a second to process these requests. And then suddenly the database starts to have failure. And suddenly when that database is failing, those requests that were taking 10 milliseconds to go against the database are now taking what? Maybe they're taking seconds. So think about it, you're going 10,000 requests a second, it takes 1/10 of a second to process these requests. That means that your server's never under really load, you're doing 10K. Suddenly, you look, and now there's 20,000 requests pending in your server, and 30,000 requests pending in your server, 100,000 requests pending in your server, and what happens to your software? It implodes. I told you guys yesterday if you're at the ACM meeting, it's not about writing software that works. Anybody can do that. It's about what happens when things are going bad, when that database is failing, when that file system is failing, when everything around you is in chaos. Can your software continue to run, handle that, deal with that, so when it's fixed, guess what? You didn't have to be woken up at 3 in the morning. Nothing went bad. You guys know that Under Armour commercial? Protect this house? That software is your house. Protect your house. You must do this from the beginning. So back pressure is when suddenly things just stop. Somewhere along the line in your software, some handoff has stopped. Think about an assembly line for a second. Imagine you had an assembly line with 10 steps in it, and all the way upstream, that 8th step broke down. The wheels broke down on the assembly line. But you don't shut the entire assembly line down. You keep moving what? Product through, and eventually that stuff just falls on the floor. This is what you're building. And so back pressure means that something is stopped. And now we have 2 things that we have to do there. We have to measure this back pressure. We've got to put them on dashboards. We've got to know, hey, there's a part of our server here that's failing. But at the same time, you've got to relieve back pressure from the system. How do you do that? How do you think you relieve back pressure from a system when things are coming in and they're stalling? So here's the third thing that everybody misses. Everybody misses at least one of these things when they're designing and architecting software that's going to be running this type of load. Number 3, timeouts, timeouts, timeouts. There is no infinity in computing. Nothing can take forever. You can. So you might have a request, and you're going to say what? You're allowed to run for 800 milliseconds. If you get your thing done, brilliant. If you don't, we're going to report back that we couldn't do it. I'm sorry, I can only do so much work, and if it failed, well, guess what? I'm letting you know. But am I going down? Am I imploding? No. That's it. Timeouts, timeouts, timeouts. Cancellation and timeouts are critical. You need to design your software with these 3 things in mind day 1. If you're not doing this, bad things are going to happen. I get called into a company in Mexico a couple of years ago. 2 guys, brilliant two kids, I mean, really, probably 10 times smarter than I am. They decided they wanted to build a chat server with Google Translate in the middle. Pretty interesting idea, right? You put Google Translate in the middle, you can talk Spanish, I can talk English, life is good. They did such a good job marketing this mobile application. Within 2 weeks, they had 250,000 users. And every 20 minutes, their server would implode. And every 20 minutes, they had to restart it. Now, I went out there, and after a week, the best I could do was watch it implode about twice a day. But they violated every one of these rules. Every one of these rules. Less is more. Less is more. Now, what I want to do is, since it's a hackathon, I want to show you some code. I want to show you how Go allows us to write software that can start up and shut down cleanly, allow us to deal with things like cancellation, allow us to deal with things like timeouts, and not just libraries that are out there to do it, actually core language features. Because remember, this language has been designed to deal with Google scale, but we don't write Google scale software, not many of us. Right? We build to. So let me show you some cool code around these ideas in Go. And what I want to do is start with this idea of what a Go routine is in Go. Just something right out of the box. Now, you guys have all taken your Unix, Linux operating system classes. You guys know how processes work, you know how the Linux schedulers work, right? How does the Linux scheduler work, right? So the job of the Linux scheduler is what? Take every single thread that's there, that's in a runnable state that wants to run, and give it time on some core, right? Give it time on some core. Do you know that prior to 2004, we considered the Linux scheduling algorithms done? What happened in 2004? 2004, what happened? Multi-core. You know when the first multi-core processors became mainstream in 2004? We were seeing threads that were in a runnable state, not being placed on idle cores. How bad is that? Think about it. You got an idle core, ready to go, and you got a thread, ready to go, and what happens? It doesn't get scheduled. It opened up a whole world of mess again. There's other things too that made scheduling really complicated at the operating system level. The hardware today has caches, doesn't it? L1 cache, L2 cache, L3 caches. And in order to get performance out of that hardware, the caches are critical, aren't they? Do you know on a typical processor, if we're talking relative, how many clock cycles does it take to pull memory out of main? On a typical hardware processor that you guys are using today, how many clock cycles? Good, 100 clock cycles. You know how many things you can do in 100 clock cycles? And you've got to wait 100 clock cycles to go get a piece of data out of main memory because you want to execute something? Alright? Your typical L1 is about 3 clock cycles, L2 is about 11, L3 can be 39 if it's being shared across those cores. And you're going to wait 107 cycles to go get a piece of data? That's unacceptable. If that was the case, your software would never run. The reality is that the total amount of memory you have to work with is the total amount of cache, if performance matters. So look at that L3 cache. There's 8 meg in there. Guess what? That's the total amount of memory you have, if performance matters. And we always say that performance matters. These things are important. So what happens there? We've got prefetchers in these caches, right? All I do is to write code to make predictable access patterns to memory, so these prefetchers can pull that data in before our instructions need it. All these things are happening. So think about it now. You have to write a scheduler. You have to take every thread that wants to run and put it on a core. But you have to deal with caches, right? Thread 1 pops up. What's the first thing that's going to happen when that thread starts running? That thread's going to start what? The process is going to start pulling in what? Cache lines for that thread. That thread creates another thread. What are the chances that thread 2 needs the same cache lines as thread 1? Probably pretty good. If we can run thread 2 on the same core that's sitting there on thread 1, then we can get away from what? The cache miss is going on. But maybe there's an idle core over there. Should we run that thread on core 2? Or should we wait for thread 1 to finish its time slice? These are fun questions to ask. What's going to give us the most efficiency? The algorithms today have to take into account all of that stuff. The algorithms are pretty amazing. Now, Go has what we call Go routines. And Go is about concurrency. You've heard the word concurrency and parallelism before? Concurrency means managing a lot of things at once. Parallelism means doing a lot of things at once. These are really two different ideas. What Go is going to try to do is say, look, let's create something called a Go routine. It's a path of execution, just like your thread. But imagine if we could run a large number of Go routines on the same operating system thread. Think about this for a second. There is overhead when you deal with threads. Context switches at the operating system level are what? They're expensive. Why? Because the OS has no clue what those threads are doing. The more threads that need to be context switched, the less time your code is running. But if we could do more on every single thread, then we need less threads. In fact, how beautiful would it be if I had an 8-core machine? I could get all my work done on 8 threads. Just think about that for a second. If I could get all the work done that I had on 8 threads on an 8-core machine, then no thread would ever need to be what? Context switched. They'd stay running at all times. How amazing would that be? And this is what Go is trying to do. Go is saying, let's keep these operating system threads so busy, and let's go with a less and more attitude, that we will create that concurrent work. Think of a Go routine as a thread, but much lightweight, that gets to run on that thread, and the Go scheduler does that scheduling. What's brilliant about the Go scheduler then is that it gets to run in user mode. You guys know kernel mode, user mode, right? There's a little bit of cost to that. The Go scheduler runs in user mode, and that's okay, because I'm going to call the Go scheduler cooperating scheduler, which is a dirty word in scheduling. But we're not asking any of you to cooperate, because when we asked developers to cooperate, it never worked out. We're selfish. Oh, I got the thread, screw you, you ain't getting it back. But it's the Go runtime that's cooperating everything. And this scheduler, even though it's a cooperating user space scheduler, God, it looks and feels preemptive, just like our operating system. And so the idea is, I don't need more threads than we have cores in any Go program that we're running. We can get it. And we can do hundreds of thousands of concurrent pieces of work across those 8 threads, against those 8 cores, and really run fast. What's brilliant about Go is that there's no magic here. Go is just using a history of computing on less is more everywhere, and pushing you towards doing the right things all the time. I call it mechanical sympathy. Didn't make up the term. But mechanical sympathy says, if performance matters, then you have to be sympathetic with the hardware. You got to be sympathetic with your operating system. You got to be sympathetic with your language. You got to be sympathetic with the tooling that you're using. Because if you're not sympathetic with it, what's going to happen? You're fighting it. And if you're fighting it, it's all over. So let me show you a couple things here on startup and shutdown of a Go program that's running multiple Go routines. Okay? Now, what this call is doing is basically telling Go, don't find those 8 cores that are in my machine. Let's just use 1. And since it's only going to use 1, we're going to be single-threaded. This is going to be a single-threaded Go program. We're going to be able to do concurrent work on this single thread. And what's brilliant here is that one thread's going to get a core, and it's going to get its full time. We're going to be able to get a lot of work done on this one thread. Now, you guys are going to be able to read this code, even though maybe some of you have never seen Go. It feels and looks a lot like C. It feels and looks a lot like Pascal. That's where its origins are. If you guys know a curly brace language, you know the syntax already. That's great, because we can have some fun looking at this code. Look up there, there's a wait group. Just think of that as some value that provides a synchronous way of synchronizing Go routines. Get 3 methods, add, done, and wait. And hundreds of thousands of Go routines can call those methods at the same time. No problem. How nice is that? Now this is going to be a counting semaphore. We're going to use this to track the number of Go routines that we have out there running in our program. What I normally tell developers is the following. Every time you create a Go routine in your software, you're becoming a parent. It's like bringing a child into the world. Because Go routines need to be managed, just like children. And I got 5 kids, all right? So if you create 10,000 Go routines, you are a busy person. There's a rule here. You're not allowed to create a Go routine unless you know when and how it's going to be terminated. Now, I'm not talking about terminating children there. Normally, I'll associate that with the following. You're not allowed to lock your house up at night until you know all your children are tucked safe away in their beds. This is a rule. You cannot lose track of your children. And so this wait group's going to let us parent these Go routines and make sure we can lock the house up at night. And so it's just accounting semaphore. There it is. I'm saying we're going to create 2 Go routines right there. And then just above that, this is the cool card. I'm declaring a function right there on the fly. It's not a named function, it's an anonymous function. There it is. And I would have executed, except I put this keyword go in front of it, which now says, look, don't execute this function right now. Why don't you go schedule that to run independent of any other Go routine that we're going to have right here. And we're running a Go routine right now, main is executing. So at that point, I got 2 independent pieces of work going on. You guys would have had to create threads in other languages using some libraries. We're getting this directly inside the language itself. And I do it again right below. So at this point, after that second Go routine there, I got 3 independent pieces of work happening, all on a single thread, all taking a turn, and that turn is being scheduled by Go. See, Go says the Linux operating system is so powerful, it's got so much intelligence. Let's not rewrite it. Let's leverage it. That's what we want to do at all times, right? Leverage what's there and build from there at that point on. So there we go. I've got 3 pieces of work. Now, notice a couple of things here. This program at the end has a call to wait. When the main function dies in the Go program, your program dies. This is nothing new. Again, you guys know all this stuff. Go is not trying to be novel. That wait call is going to hold it until those other Go routines report that they're done. How nice is this? I mean, look at this code. It's really something that all of you can read here. So I've got 2 Go routines, one that's displaying the alphabet in lowercase, one in uppercase. It's going to be independent work. We're holding this main function until they report what? Done. There it is. There's the call. You can read this. And we're using closures, by the way, to get to that WG variable. Notice I didn't have to pass it in. Again, it's really making the code readable. I'm always talking about simple, reduce, modify, readable code. There it is. And I can take this code here. We can run it real quick. We'll make some modifications to it. We'll build it. We'll run it. Nothing spectacular right now, but what you might realize is that the second Go routine that we created, which was from uppercase, ran first. Now, even though it's a cooperating scheduler, I always want you to think of it as preemptive. It is undeterministic. That's important. But you can see that that first Go routine got to run, and then the second one ran. Now, I can turn this into a parallel program just simply by making one change here. Simply by just saying, let's run with 2 threads. Now, each Go routine that we created will get its own thread, which will be on its own core, and it will all run in parallel. All I've done is made one change to the program. What is it? 2. So we'll look at the output now. You start to see a mix of lowercase and uppercase letters. And it's random, it's not predictable, we couldn't even tell when that's going to happen. Within a few lines of code, I got a program that starts up and shuts down cleanly. I've launched some independent pieces of work. I'm managing that work, and everything is clean. How cool is that? And I'm not showing you code that we don't do every day in a Go program. This is how we manage Go routines in many, many, many cases. But I now want to just show you quickly some of the channel semantics that are in Go. Coordinating Go routine, or coordinating threads in general is hard. If you've ever tried to do that using atomic instructions or mutexes, I mean, those constructs are about synchronizing access to shared state. Coordination is a completely different problem. So Go has added as part of the language the ability to coordinate or orchestrate a routine. So let me give you some channel semantics first so you can see it. And then let's do something bigger with it so you can get a sense of how we can put these pieces together. I'm really big on mechanics. I think if you're going to learn anything in computer science, you want to get a sense of history around it first. Then you want to learn mechanics. I always take it like, you want to learn how to use a hammer. Well, we need to understand the mechanics of that hammer, what are you going to do, and then you want to get into design. When do we hold the hammer in the back? When do we hold the hammer in the front? How do we use that hammer in the best ways possible? That's design. So let's look at some mechanics here. Now, a channel is a data structure. It does have mutex underneath, but what it does is it allows us to do one thing. I always want you to think about this when we talk about orchestration and channels. The word is signaling. Signaling. A lot of people like to think of channels as a queue because you can put data in and data can come out. And the order that you put it in is the order that it comes out. But you're going to make a lot of mistakes if you start thinking of this as a data structure around queues. I want you to think of this as a way of signaling another Go routine that it's time to do something. And sometimes that signaling comes with data, and sometimes that signaling doesn't. So let's take a look at this code here. That make call is just making the channel so we can use it. And the channel at this point can only work with string data. Go is very type safe, so we're going to be very specific about the data that we can move around. And we said we can move string values across this pipeline, this channel. Now, if you notice right there, what am I doing again? I'm creating an anonymous function. I put the keyword go inside of it. That function is now off on its own. And then we continue down to that print to the standard out. And I've got some weird things going on with the channel variable and these arrows. So there's two types of channels in Go. There are unbuffered channels and there are buffered channels. Now, unbuffered channels are really special. They're special because they give you guarantees around signaling. Let's say I needed to talk to you and I said, hey, I need to make sure that you get this information. See, the unbuffered channel gives me the opportunity to know that my friend here, Ian, he got it. There's no ifs, ands, buts about it. Because we both have to come together, the handoff has to happen at the same time. And what we say there is that the receive, if he's receiving data, the receive happens before the send. I now know he got it. I love unbuffered channels because that guarantee that the other side got the signal can give you a lot of reliability. But I told you nothing is free, right? I told you guys nothing is free. To get that guarantee, the cost is latency. Think about it. If I want to give Ian this piece of data and Ian decided to oversleep because he was partying hard last night, and it has to be a guarantee that I give it to him, then what? I'm stuck here in the cold, cursing Ian out for the next half an hour, calling him up over and over and over again because he didn't show up. I'm stuck. But if I need that guarantee, do I have a choice? No. And there are ways of doing cancellation where I finally say, forget about Ian, man, I'm done with him, and I can walk away. Okay? But I know at that point Ian either has it or he doesn't. Right? He's done it or he's not doing it. That's the unbuffered channel. So let me tell you a really quick story, okay? So I'm rarely home in Miami because I travel quite a bit, and I get home and I decide I'm going to go to the office. Now I haven't been going to the office that often because the traffic Miami's got out of control. But I told my wife, I'm going to go to the office today, and she says, oh, that's great, you're going to the office. I have this letter that I have to give to my business partner's wife. Can you, when you get to the office, give this letter to Ed? I said, honey, no problem, just give it to me, I'll give it to Ed. She stops and she goes, you know what, forget it, I'll mail it. What are you talking about? You're going to forget, and this is important, and she's got to get this letter, and you're going to, I go, honey, want my chocolate liver? Give me the letter, I'll give it to Ed. Like, what's going on? And then she says, okay, I'm going to give it to you, but she's not looking really convinced. And Then she asks me if I'm going to take my son to baseball practice. Well, one thing I've learned, that my wife's children are not allowed to be late to activities. My wife's children, when it comes to activities. So if I tell her that Tom is going to be at baseball practice at 6 o'clock, and I got in trouble for this before, this is sad, this is a rule, this is done. I haven't been around, so I'm trying to be Superman right now. Honey, I'll make sure he gets the letter, and I'll make sure Tom makes the baseball practice. Now in Miami, when you walk into an office, any office in Miami, there's a ritual that happens. You gotta have Cuban coffee. Think of the strongest espresso you've ever had, double it, and kick it with some sugar. So you only drink this much. So I get into the office, what happens? Cuban coffee time, an hour and a half goes by because all you do is bullshit. Oh yeah, Cuban coffee. And I go back to my desk. What did I forget about? The letter. Now, I know I have to leave the office by 5 o'clock because if I don't leave the office by 5 o'clock, Tom is not getting to baseball practice on time and I'm going to get in a lot of trouble. So it's about 5 to 5. Remember cost trade-off. What's the cost trade-off here? Getting my ass kicked or not? So I decide to pack up my stuff. I'm about to get out of the office, and what do I see as I'm packing up my stuff? The letter. Now I'm freaking out because Ed usually leaves at 4 o'clock. So now I'm panicking. Now I'm trying to make up some excuse why I can't get home, right? I said, no, I'm not going to do that. I run into the office. I run into the other side of the office. Ed's laptop is still there. I said, this is brilliant. I'm asking everybody where Ed is. Nobody knows where Ed is. So what do? I take the letter and I put it on Ed's laptop. And I tell the guys, make sure Ed sees this. This is important. He's got to get it. I run out the door. 12 moving violations later. I get home. I tell Tom to get into the car. We get to baseball practice. 2 hours later, I get home. It's 8 o'clock. The first thing my wife asks me as I get out of the car is, did Tom make it to practice on time? Now, whether he did or not, the answer is what? Yes. Now, she has ways of finding out, but again, I'm willing to take this risk. And then she says, did you give Ed the letter? I say, oh, come on, honey. Come on now. I'm Superman here. Ed got the letter. Tom got to practice on time. We're good. She's still looking at me like, but she says thank you. Now 2 hours go by, I'm laying on the couch, I'm watching TV. Now my wife's a 5'2" Italian. If you've never met an Italian before, they can be a little feisty. You guys see The Godfather? Yeah, it's like Michael Corleone, but a woman, when she's pissed off. And she walks over to me on the couch, and she's like this, hands underneath her armpits, she's looking down at me, she's pissed off. I just look up and I say, honey, whatever just happened, it wasn't me. She says, you didn't give Ed the letter. What are you talking about? You didn't give Ed the letter. I just talked to Alex. Alex don't have the letter. She just talked to Ed. Ed don't have the letter. You didn't give the letter. Now, I'm scared for 2 reasons. 1, I can't get a word in. And 2, I can't see her hands. So I do the only thing I can do. I jump off the couch, I beat my chest, and I yell, I gave him the letter, damn it! And I walk out of the house, boom, slam the door, and just being thankful that I'm outside. I may not get back in, but I'm alive. No marks. So I call up Ed, and I say, Ed, I left that letter on your desk there, man, right on your laptop. There's no way you missed it. Please tell me you have it, you just forgot to give it to Alex. And what does he say? He says, what letter? Now, who's still responsible for this letter? Ed's got complete deniability. Right? Did I give Ed the letter? Well, the reason I'm telling you this story is because this is what best describes what a buffered channel is. And the risk in using a buffered channel. Think about it. When I used the unbuffered channel, there was the guarantee that the signal was received. But if I use a buffered channel, and I put that piece of data in the buffer, did I have any guarantee that it was coming out the other end? It's not that it's lost, but I have no guarantee that somebody on the other side got it. So what's the cost trade-off of the buffer? Lower latency, because I don't have to wait, but we're walking away from what? The guarantee of the signal. So most of the time, if I see code that's using a buffered channel that's greater than 1, it starts throwing big flags in my head. I start freaking out. Unless we're doing fan-out patterns, where you know you're going to throw 20 coverages at a problem and you know they're going to come back. When you know exactly how many of something you need, then you're good. But when you have no clue of how many things are going to be involved, it gets very, very scary. And so I told you again, it's always about cost trade-off, right? So higher latency, guarantee. Lower latency, less guarantee. And the larger the buffer, the more risk around potentially not knowing how things are going. So if we come back here, this is an unbuffered channel right there. There's no buffer size associated with it, which means sends and receives have to come together. Now what you see here, right inside that anonymous function, is the send. The arrow is pointing into the channel. It's a binary operation here. We're saying, hey, send. This isn't I/O, so we don't read and write. But what we're saying is send this string into the channel. We know that's going to block. This is unbuffered. We have a guaranteed signal here. This is what we're looking for. So that go routine now gets scheduled to run, but now it's in a sleeping state, waiting for somebody to come along to receive it. And now, what do we have there on the next line? Inside the print line function, you see the arrow again attached to the left-hand side of the channel. What this is saying is, I'd like to receive a string. So now, when the scheduler sees go routine on the send and the go routine on the receive, the exchange takes place. The receive happens before the send because that gives us the guarantee. Just there. This isn't some API. This isn't some extra package. This is built into the language. And so we can run this code. It's not really exciting, but we'll see. Hello. I told you that signaling can come with data or without data. You don't necessarily need to always use data. I want you to think about signaling, not this being a queue, not this sharing data stuff. We have somebody else on the other end that needs to do something for us, and either we need to know that they've received the signal or not. Data is just an artifact of maybe being able to process that signal. But look at this. What you're seeing here on the channel, again, is an unbuffered channel, and we're using a special type and go called the empty struct. The empty struct is interesting because I can create 100 million values of this empty struct and there's zero allocation. There's like an 8-byte value that's associated with it. Now I'm using the empty struct because this is going to be a signal with no data. I want to signal some event. So look at what I'm doing here. The go routine gets created, it waits 100 milliseconds, then it says, I'm gonna go signal this thing, and it closes the channel. But even before all that happened, down there we're doing a receive. So that receive's gonna block until there's a corresponding send, or if you close the channel. And you can only close the channel once. But I could have 100,000 go routines on that same channel receive, close it, and they all get notified. And it's guaranteed. I know they're all going to get notified. That's just part of the mechanics. How cool is that? And this is how we can do cancellation in Go. Imagine you had a web request, and suddenly as part of the web request, you go and you say, I'm going to make a database call here. And that database call is taking a long time. And you say, no, after 800 milliseconds, we're done. We can use this close mechanism to tell the Go routine that's waiting on the database call to what? Dude, you're done, move on. And if you can cancel that network request, do that too. So cancellation is really important. We told you that's one of the foundations, right? Start up and shut it down cleanly, back pressure, and timeouts, cancellation. These things all have to be architected in the same systems. And so right here, as soon as that go routine closes the channel, the other go routine moves on. Again, built into the language. And you guys can read this code, right? There isn't all this mutex and atomic flagging going on. You can look at this and read it. Remember I was telling you guys yesterday about what? What is number 1? Integrity. What is number 2? Readability. Always trumps everything else. It's all just trade-off now. Latency versus guarantees. What do you need? What do you need? All right, here's another mechanic right here. Now sometimes you might want to signal something with a piece of data, and then you might want to wait to know they're done. You see, on the signal, it's just a matter of going, hey dude, can you do this? And he takes it, But all I know is what? All I know is he's got the signal and he's working on it. But what if I need to know when he's done? You can tell me. Here, look at this. So here I am right there. I'm that go routine in the anonymous function. What am I doing there? It looks like I'm on a receive and then a set. So I'm blocked. I'm waiting for some work to do. I've launched this go routine, waiting for some work to do. This other go routine down here, that's me down there. What do I say to him? Go do this, right? Go do this, and then I wait. There's the receive, send receive. And then, what happens here? So here's me. Hey, can you go do this? Now I'm waiting for him to switch and tell me that he's done. His receive hits, and he says I'm done, and then I move on. How cool is that? So now that's a situation where like, go do something, hey Bill, and we're signaling each other back and forth using a little piece of data. Now here's your first buffered channel. It's a buffered channel of 5, and if you notice here, what I'm doing is I'm loading the entire buffer up with some integer values just to make it full. Now, when you perform a send on a buffered channel and it's full, it's going to block just like an unbuffered channel. There's no room. Or if you go to do a receive and there's nothing to receive, it's going to block. There's nothing to take. But while there's room or there's something, we get to reduce what? Latency. A lot of people hate that word latency when it comes to algorithms, right? Latency can really cause a problem. Networking latencies in particular. So we always want to look to reduce latency. So here's this buffer channel. We load it up with 5 integers, and I immediately close the channel. So here's a channel with data that now closed. Notice I don't have any extra go routine here. All this is happening on the same go routine. Now that for loop in Go is interesting because for doesn't have the keyword while. It does everything with the keyword for. But look at this for loop here. We're ranging over a channel. Basically what that means is keep iterating every time there's a piece of data to receive. So it's going to receive 5 pieces of data because we put 5 pieces of data in there. And then once that range notices that the channel's closed, terminates. How cool that is. Again, this is all about what? Readable, clean code that's being driven from the language itself, not through APIs. Can you guys start to see some of the power here in writing concurrent software, in orchestrating things, and then being able to leverage the minimal number of threads possible to get all this work done? Because if one go routine blocks, suddenly the scheduler can put another go routine on the same thread. That thread doesn't have to be context switched out. In fact, what's really cool about the Go scheduler, if it ends up seeing a thread that is no longer busy, this is cool. If suddenly this thread, which is on some core, currently doesn't have any Go routine work to do, you know what the scheduler does? It spins it just for a little bit. Spins it just a little bit. Why would the scheduler spin that thread? Even for a little bit. To keep it busy so the OS doesn't what? Context switch it out. In the hopes that another Go routine comes in and we keep going. Close it. It's like, yeah! That's awesome. That's not going to spin forever, obviously. Right? But when less is more, less threads, right, doing all of this work, can you start to feel, and with the language mechanics that I'm showing you, how cool is that? All right, let's do the following. Let's do the following. When we act on some code, right? Alright, not bad. Hello, Potsdam. Silly little program. But it gets us going. Let's do the following. I always like doing this demo, and I can do it in about 10 minutes. Let's pretend that we were Google, we wanted to build a search engine, we wanted to hit, even though they really don't do it this way anymore because it'll be too efficient. So let's just pretend. we wanted to send that query across multiple servers, and whichever one came back first, well, that's the result that we're gonna set, okay? And we can do that regionally, right? Across a couple of different servers, not the entire N number of servers, but 2 or 3. Whichever one comes back first, that's the one that we'll give to the user, and we'll throw the other 2 away. This is a great problem around concurrency, because we can start 3 independent searches against 3 different servers, and then deal with what's coming back. So how can we do something interesting like that? Well, let's do the following first. Let's create a struct you can think of like your classes, except there's no behavior, it's pure data. Let's just pretend it's a server struct. And let's even pretend that we have a host in there, right? We've got some information, we gotta know which host we're gonna talk to. And let's even pretend that this server here has some behavior called search against that one. Maybe there's some term that we use. And for now, let's just pretend that this thing's going to write out something like found. And let's even just make it so we can do something here. Give it some ID, so we can do that too. We'll build on this. The green line's going up because I'm going to comment on that. And the linter that I use wants nice comments because this also becomes part of documentation. So we'll ignore that for a second. Now we'll do more here. Let's also add a little timeout here, just so we can have some fun here. For now, I'm just going to do time.sleep just for now. We'll continue to add to this. We'll have to wait 100 milliseconds. All right, so I got this search. Imagine an implementation now silly, and we'll add to it, but it's going to go out. Let's pretend 100 milliseconds it came back, and we're going to go just try to say we found this result. There it is, there's some ID. And now that I've got this server here and I've got this, let's do the following. We'll just keep it really simple as well. Let's just go ahead and we'll create a server, and there's some host name there. Maybe what we'll also do is give it an ID instead, so we can really leverage that. ID, which means we don't have to pass it in, it's part of the server, we're making it simpler for now. And we'll just say that the ID here is 1. Server 2, we're going to get this to a concurrent place, but ID 2, server 3, ID 3, okay? And doesn't like anything I did here. This is part of writing code. So what it's complaining about is that I haven't used these variables yet. Go is very saying, hey, we want to write readable code. If you create a variable and you're not using it, that's just pollution inside the code, right? So just to keep it simple again, just so we can get something going here, let's run search, term, standard pairs, search 1, search 2, search 3. And this code hopefully will just run. Here we've got our server, we've got some search, we've got this, it still has bugs, so let's see what we've done here. Undefined ID, right. We'll talk about that later. You actually shouldn't have a problem with that. Oh, it would help if it was an integer. Okay, so that's all good now. And it still doesn't like line 12, of course not, because that would have been too easy. And that's on the S value there, so now you should be good. Now we run. Okay, 1, 2, 3, it ran in series, not really exciting. So the whole thing was going to take about 300 milliseconds. But let's run that concurrently now. Right? Just real quick now. One could argue all I have to do is run. I could just put go in front of all of these calls, and they would run. But what's going to happen if I run this code? Am I going to get any output? No. Why didn't I get any output? Because when main terminates, the program terminates, I launched 3 coroutines, but did I wait for them to finish? No, I didn't at all. So let's fix that real quick. We probably should use a wait group for this, right? Let's use that wait group again. Let's for now add three is going to run these three coroutines, and then let's do the following. Let's say func. We'll run this code here, then we'll say you report that you're done. We'll do this, and just to speed this whole thing up. You'll do 2, you'll do 3, and then we'll wait. So if all that worked out well, we're getting that we have to actually make the function calls here. There we go. I still have one more problem at the end which I'm happy with, and that's because this is a type, so we're going to do that. Now everything looks good. And now it ran, we saw how fast that was. We only had to wait a total of what? 100 milliseconds, and all three ran. That's kind of cool. I haven't done that much work yet, and I have 3 independent searches going now. But the searches are right into the screen. So how cool would it be if the search actually returned the result for us, and then we'll go display over here? That would be kind of cool. So let's make a quick change here. I don't want this function here displaying it. I want it to go find the result, and I want it to pass it back to us. And the best way to pass that data back is over a channel. So we're going to need some sort of channel. Now, maybe what we can do is put that channel in here, right? So maybe some result channel, which will be this type string. That would be cool. But channels have to be initialized. They have to be initialized properly. So let's do the following. Let's just add a quick new function. New functions return new servers. And what this function can do is create that server. And we can pass that ID into it. ID is the ID. And now I can make sure that this channel is made. So that's pretty cool. So now I've got a factory function, is what I would call it. It creates servers that are ready to be used. There we go, I've got my new. Now, if I don't do anything else right now and just apply this new idea, then what I'm going to want to do is say, give me a new 1, new 2, give me a new of these 3. This code, hopefully it should still work. It does. That's fantastic. And now that I have that, the idea is I want to use this channel that we're going to have here. Just make that capital. And I want to do something different here. So in this case, we know that this is the result, and we want to send found to this, and maybe it would have been nice to send that S1 ID too, right? So let's do the following, func.s printf, and we're going to do s.id, and then found, and that will be our string. And then it's done. So we're going to pretend that I found it, and then what are we doing? Signaling back that we found something, and here's some data that will be associated with it. And there we go. And now what we're going to do here, we like this call, so let's see what it's saying here. I'm using sprint. I don't need that, I just need sprint. There's a formatting going on. And now, what do I want to do here? When I call this search, okay, that's fine. We're going to go off and call search, but we need to be able to get the results back. So maybe we can do the following now. Since I'm going to wait for all 3 of these results to come back for now, I can probably get rid of the wait group, right? I can also probably just simplify this even more. Say, hey, you go do this. Let's run these 3 searches. Now I still have to hold main, right? But maybe I can do that in a loop since I know there's going to be 3 right now, just to keep things simple. I plus 3, I plus, and then what are we going to do here? Maybe right inside the print line, we can just do a receive on every one of these. Now, actually, when you think about this, I kind of put myself in a little hurt when I think about it. Because I have these 3 unique variables, right, that I have to deal with. So maybe it would be better to just quickly, in the few minutes that we have left here. Actually, we're running out of time, so. Ideally, what I want to do is put this into an array of some sort, right? And I can loop over that array and get what? Get those results. The key here was I wanted you to start seeing how Go has built this stuff inside the language itself. It's not an external library. It's not something outside the language spec. And you saw how quickly I just started refactoring. And this is really important. This is what I teach every single day. Solve one problem at a time. It doesn't have to be the final solution. I wanted to be able to hit 3 servers and just get results back. What did I do? I wrote code that hit 3 servers and got a result back. Then I said what? It'd be nice to run that concurrently. I ran it concurrently. Then I said what? You know, it would be cool if we can get the results back from each one. So what did I do again? I refactored again. And I made sure that worked. And then I was going to make another refactor. And I'm going to make sure that works. And then I'm going to refactor again. And I'm going to make sure it works. And by the time we're done, you're not guessing, right? If I started out originally with, let's run all this stuff super concurrently, and I started there, you're never going to get it. You just won't. I want you guys doing that today. I want you to say, this is a problem we're going to solve. These are the little problems we need to solve. Solve each little problem and refactor to solve the next ones and refactor to solve the next ones. I know refactoring might seem like, Bill, you're making me write code over and over again. You will get done faster. Because by the time you write the last piece of code, you already know it works. You're now not spending time debugging because you've built on what you know works over and over and over again. So I hope you guys got to see a little bit of Go here. I try to hack a little bit of code at the end. The design principles are much more important to me than anything else. You can learn code. Design principles are key. So your servers have to do what from day one? Start up and shut down. Under load. I don't care if you got 100,000 requests a second going through it. Signal it to shut down and make sure, even if it takes 30 seconds, you make sure that goes down. Back pressure, back pressure, back pressure, back pressure. Understand your back pressure. Monitor the back pressure. A little bit of back pressure is good because it means your system's in balance. A lot of back pressure means your system's about to what? Implode. It's taking on too much work and it's not getting it done fast enough. And 3, timeouts and cancellation. Timeouts and cancellation. Nothing can run forever. How long are you willing to wait? Sometimes the user has to tell you, sometimes you mandate that. Timeout and cancellation is everything. That's what keeps the system healthy. All right? And play with some Go, and if you want to play with some Go later, I know you guys got projects, just hit me up. We can hack on some more stuff here. It's really good. And if you decide you want to try to do a small piece of what you're building in Go, come and find me. You know, I can point you in the right direction. Can't write any code for you. But I can point you in the right direction. There's a lot of good stuff out there. Thank you for spending the entire hour.